Hi. So we're going to go over 5.3 centripetal force, and this is going to be quite simple. Well, at least the first part, but it gets a little bit more nuanced later. So, first, let's talk about force using acceleration. Remember Newton's second law, F equals ma. So acceleration here is just m, and then the acceleration force, or centripetal force here, which will be v squared over r. I'm gonna explain that this isn't a fundamental new force. It's more like a role that a force plays. So imagine that you have the Earth orbits around the sun. I don't think in a perfect circle. Probably like an ellipse of some sort. I don't really know that much um, astronomy, so I can't really say for sure. I'm not a astrophysicist, but I do know that gravity is the reason that the Earth orbits the sun. So then gravity would basically be a centripetal force here, although technically it's not a perfect circle or perfect circular. I don't think it's constant velocity all throughout. But regardless, centripetal force is a role, and it's something that friction could play. It's something that a tension force could play, and in the Earth's case, a gravitational pull. So let's go over a tire example. So, what happens when a car turns the tires to go around a curve? Well, if there was no friction, the tires would simply shift and the car would continue to move forward. Sorry, this would be the centripetal force proof or acceleration proof. So what happens is, let's just say we have this road here. I'm not going to draw the outwards road. So let's say we have the car, and I'm going to try to draw it from the outside, but I'm not really a good drawer, so, okay, well, I guess we'll draw the tires. So if the tires are like, I'm not really good at drawing either. So let's just say the tires are like this. Actually, let's just draw one tire. And let's say the tire is going this way. Well, nothing is stopping it because this is just a horizontal force. So Fx, yeah, horizontal force, it would just keep going this way. However, what happens if the car right here decides to skid or turn the wheels? Now the wheel's probably going to look something like this, where it's kind of rotated a little bit, and friction starts acting against it because it's parallel to the ground. So the friction is stopping this car from just going straight forward. And in fact, the wheels are just gonna, there's a friction force applied to the wheel, and that acts as the centripetal force. It's a little bit difficult to understand, but simply put, when a tire turns, if there was no friction, sorry, I'm like just such a horrible drawer. I guess we'll draw it from the front of the car. So let's imagine that this is a car here. um, and the wheels are like this, it can just continue going forward. But once the wheels turn sideways like that, there's a force being enacted on it because the force is parallel to the ground, and that force is pushing the car inwards because it acts as a force resistor, which allows the vertical force to continue to be applied, and pushing the car forward while the friction applies it this way and allows it to turn. So airplane making is a little bit simpler, in my opinion, to explain. So I'm not gonna draw the airplane because I'm not a good drawer. So we have and we're assuming that this plane is homogeneous, or it's the same all throughout because there's a 1/2 force on both sides, which probably isn't true in real life, but we're just gonna use it. So this is called the flight force, and it's going to be acting upwards. So L should be equal to mg, because mg is, because that's what's keeping, like, imagine this plane moving, and not, so like let's say this is the plane right here, which I'm going to draw as a box, and let's just say it's going this way. That means gravity and L must perfectly cancel out. So the weight and the I believe it's called the upwards force here, or the lift force, are canceling out because this plane is not moving downwards. So that means the forces are canceling out, meaning that the movement is not adding. And that's the third law, I believe. Wait, no. Yeah, I'm not sure. But the forces are canceling out, so the net movement would be zero downwards. Well, what happens if the plane rotates? And we'll come over here and we'll do that. So now the lift force is not perfectly stable, or is not perfectly upwards. Um, the lift force would still be, I believe, one second. The lift force would now be still upwards directly. So now we have to use some trigonometry. And what happens is that the lift force goes this way, which I guess it's the same thing relative to the other position, because this is still upwards towards the wings and this is upwards relative to the wings as well. So what happens is, oh, sorry. Um, if we draw in here and denote an angle right here, where the plane rotated this many degrees, so I guess that would be theta as well. Um, this vertical force would be L sine theta. Wait, no, yes, L sine theta, because if we drew a triangle here, um, this would be L sine theta, and then, I mean, I'm sure you guys know trigonometry, L cosine theta. And that will, this is the centripetal force, because the L cosine theta is simply keeping the plane up, while the L sine theta is the force that is pushing against the vertical, or the horizontal. And remember that there is no horizontal force. There's a vertical one, which would be gravity. Pretty simple. Here is a higher explanation, but I just explained it. So that's basically all of centripetal force. This is a quite complicated chapter if you actually try to understand everything behind it, because wow, the mechanics are quite interesting. But that's 5.3, and 5.4 should be slightly easier since we're just dealing with basic trig. So